Let's walk through our standardizing formula here, and technically I would do this in about 4 steps here, and I'll walk you through those 4 steps, which hopefully will help you figure it out. So your first step would just be to write out everything that you know. So in this situation, I know that my mean is going to be 50. I know that my standard deviation is 10. And I want to know if my score will be 70 or above. So my x is going to be 70. And another way to write this out with my mean and standard deviation is we're going to assume I have a normal distribution because that's what I'm working with. So you can write it as normal and then your mean, comma, your standard deviation. So you'll see that notation every once in a while. And it's just a way to say that your data is normal and it tells you what your mean and standard deviation is. So that would be what I would do for your first step. Your second step, I would standardize. And when I say standardize, I mean use your formula. And to standardize, we need to find x minus mean divided by standard deviation. So for part 2, we're going to standardize our formula. We're going to take our x-score, subtract our mean, and divide by our standard deviation. And just a quick notation thing, our x-bar represents our sample mean, our little s represents our sample standard deviation, and we know a sample is the smaller group. Sometimes you may see this written in population form as well, and it means the same thing, the only difference is it'll have different notation. So it may say x minus mu divided by standard deviation. The mu represents your population mean. Your sigma represents your population standard deviation. So those are just a couple of notations that you want to remember. So to do this, we are going to sub in our 70 for our x, our 50 for our mean, and we're going to divide that by our standard deviation of, our standard deviation of 10. And that will give us our z-score. So 70 minus 50 gives me 20 divided by 10. So I'm going to get a z-score of 2, or I'm going to write it down here. We're going to get a z of 2.00. And the 0.00 isn't important as long as you remember it, but our z table goes to 2 decimal places, so I always write my answer in 2 decimal places so I know what I'm looking at. So that's what I do for our first 2 steps, is write out what you know, and then go ahead and standardize your formula. I'm going to write that down here just so you know, standardize. Once you standardized it, you're going to want to look up the z-score in the table and actually look at it on a graph. So before we look it up in the table, I'm going to graph my z-score of 2. And to do that, you're going to draw a normal curve. And this is more for your benefit, which will hopefully help you. But with a normal curve, our mean and median are all in the middle. And when we're looking at a normal curve, we usually just call that our mean. But it should cut your graph completely in half. Ignore my horrible drawing and assume that's cut directly in half. If you get a positive z-score, that is to the right of your mean. If you end up with a negative z-score, you will look to the left of the mean. So this one, we've got a z-score of 2. And what that represents is that we're 2 standard deviations away from the mean. So as you saw in the empirical rule earlier, we have usually about 3 standard deviations and then very little left in the tail when you're looking at a normal curve. So a z equals 2 is our 2 standard deviations, which is approximately right here. So z equals 2. And if you go back to the original problem, we want to know the probability that it will be 70 or above. And that or above tells me that I am looking at greater than. So I want to look at what is the probability that is greater than 70. So all that's greater than 70 is the proportion of my normal curve to the right of the 2. And that's this little area shaded right here. So that represents any value greater than 70. So to do that, and to actually figure out what proportion that represents, we need to look this value up in our table. And your table is in the back of your book. It's table B1. It's on page 368. and 369. I think it covers a couple pages there. And I'm going to just scroll over here. Remember, we got z equals 2, and I'm going to go to my next slide here. And I took a picture of that piece of paper, so excuse me, it's not super clear. But what you want to do is you want to look under the z-scores column to find that z-score. In this situation, we found a z-score of 2.0, which is right there. And I want to look at the z-score number associated with that. So this is the little section I'm looking at in my table. I got a z-score of 2.0, which represents the number of standard deviations I am away from my mean, which will help us figure out our actual proportion. So the area between the mean and the z-score is 47.72. So remember that, the area between the mean and the z-score is 47.72. So the area between the mean and the z-score, so this area right here, is 47.72? We're going to go back real quick. 47.72. And that represents from the mean to my z-score. So this chunk right here is 47.72. Now we want to be able to figure out what our black shaded region is here. Well, if you remember from earlier this chapter, the normal curve represents 100%. Okay? And our mean divides our normal curve into two perfect halves. So if it divides it in half, the first half is going to be 50%. Okay? So we want to figure out what's left over on this tail. There are a couple different ways to look at this depending on what you prefer. We know that it adds up to 100%, so one method would be to add up. We've got the half that's not shaded, plus we've got that 47.72 that's also not shaded. So if I add those two together, 50 plus 47.72, you would get a score of 97.72. That tells me that 97.72% of my graph is not shaded. Okay? And then to figure out what is shaded, I would take 100 minus that. Which leaves me with about 2.28% remaining. So about 2% of my graph lies in that little tail. Another way you could do it is just look at the right half of our graph, and we know that that's all 50%, so we could just take our 50 minus our 47.72. Either way, we are looking at only about 2.28% of our graph is greater than 70. So you would answer that 2.28% of the data is greater than 70, which should answer your original question.